Okay. Okay. So let us recall what we are doing. So recall. Okay. So we are considering this problem. Laplacian u equal to f and u equal to g in BR and on del BR. So this domain has a symmetry, right? Rotational symmetry. A rotational symmetry. Okay. So, and given that f and g are radial function, f and g are radial functions. Okay. Then we can look for a solution. We can look for solutions which are radial. Right? So for that reason, we first define, that means we are looking, we are looking for a solution which is of this form, mod x. U of x is u. Sometimes we write down as a, because this is the abuse of notation, because this domain of these two functions is different. So sometimes we write it like this. Right? So this is the radial function where mod x is equal to r. So it depends on the mod x, not on theta. So you can see that if in R2, if you see, it depends only on the radius. Okay. So how the Laplacian of u looks like? Can anyone tell me? Laplacian of u in, if u is of this form, then Laplacian of u is equal to phi double prime r plus n minus 1 by r into phi prime of r. Yes or no? This is Laplacian of u, that phi double prime r plus n minus 1 by r phi prime of r. So the problem now, if ux is equal to phi of mod x is a solution of the previous problem, then we should look for v. Then have phi double prime of r plus n minus 1 by r phi prime of r is equal to fr. It's 0 less than r capital R, and we know at the boundary phi of r is equal to g of r. And I said something on phi prime at 0. This you don't have to understand now. Okay, don't have to understand now. Okay, so this equation, the PD reduce this Laplacian u equal to f, u equal to g. This PD reduces to this. If this has a domain, the domain has some spherical symmetry or rotational symmetry, f is a radial functions, then we can look for a solution u which are radial, and then this PD will be transformed to an ODE. Okay, so this is something. Okay. Now let us look for a, so now let us start a new topic and let us look for a, this is a very important thing. Let us look. So if you have any problem, you can ask me. Okay, this is very important in the PDE theory, what I will be doing today. Okay, if you have any question, you can ask me. Please, let us look for radial harmonic function. What is the meaning of that? What is the meaning of that, Shammi? What type of solution I'm looking for?
Like it satisfy the Laplace equation and
U equal to 0 in Rn, something like that, and u is radial. Right?
Yes, sir.
So why I can consider a radial function? Can anyone tell me? Means why I can seek for a radial solution. Rn has a rotational symmetry. Yes or no? It's a symmetric, right? Yes or no? The orthogonal O of Rn is what is O of Rn? Orthogonal transformation is equal to what happened?
Rn.
Rn, yes. Orthogonal transformation. And also I have given you a problem. If I define V of x equal to U of O of x, then Laplacian of V is nothing but Laplacian of U at the point O of x. That is, so this is equal to 0. So if this is 0, Laplacian V is also 0. O of x, that means nothing. O of x is nothing but this. Okay. So we can look for a radial solution of this equation. Yes or no? Yes or no?
Yes, sir.
Yes. Now tell me, so the equation just using our previous computation, from our previous computation, you can conclude, u is nothing but u of x is your now phi of mod x. So what is your Laplacian of u? Laplacian of u equal to 0. This means phi double prime r plus n minus 1 by r into phi prime r is equal to 0, provided r not equal to 0. Yes or no? Yes or no?
Yes, yes, sir.
Okay. Now this I can write r not equal to, I can multiply the equation by r to the power n minus 1. So r to the power n minus 2, I think. Yes. Phi prime of r equal to 0. R not equal to 0. These I can write as r to the power n minus 1 phi prime of r whole derivative of r equal to 0. Yes or no? Yes or no?
Yes, sir.
Yes, yes.
So what will be the solution? This is equal to what I can write now? R to the power n minus 1 phi prime of r is equal to, just I integral. This is C1. Yes or no? For r not equal to 0. For r not equal to 0, I can write this imply phi prime of r is equal to c by r to the power n minus 1. For r not equal to 0. Yes or no? Yes or no?
Yes.
Okay. Then what will be phi of r? Please tell me. क्या होगा phi prime phi r?
For n equal to 2, it will be c times log r plus d.
It will be yes. So very good. This will be c. Let's say c1, c2 log r plus c1, or c1 log r c2 for n equal to 2, and for n not equal to 2, c1 r to the
R
power
raised to n minus 2 plus
yes,
c.
n greater than equal to 3. So, and also this is important, that has to be, this you have to understand, that this for r not equal to 0. So you have solved the equation Laplacian is equal to 0 if u is phi of r, that means you know what is the meaning, and we know that the harmonic functions are c1 log r plus c2 if n equal to 2, and c1 by r to the power n minus 2 plus c2 if n greater than 2, for r not equal to 0. So you have solved all the harmonic functions. So what is the harmonic function? Laplacian of phi r is equal to 0 for r not equal to 0. This equation you have solved, right? Yes or no? Yes or no?
Yes, sir.
Yes. This has a special, I will tell you later why. Now I define with this motivation in your mind, let us define a function. You see what is this function? This is known as fundamental solution. This is the fundamental of PDE theory. What is that? Fundamental solution. The function phi of x minus 1 by 2 pi. Why I'm writing this, you will understand later. I will tell you. N equal to 2 and some constant n into n minus 2 into alpha n. What is alpha n? Huh?
Volume of unit ball.
Exactly. Of 0, 1. So I define a function phi x is equal to minus 1 by 2i log mod x if n equal to 2 and 1 by, this is a constant, this you can say constant Cn. This is a constant Cn, this is a constant C2 for 1 by mod x n. This is called the fundamental solution and this equation is defined, this function is defined for x not equal to 0 and rest of the place we can define this function very nicely. For x equal to 0 I cannot define because log mod x also is not defined and of course x equal to 0 1 by mod x is also not defined. It's called fundamental solution. It's called fundamental solution of the Laplace equation. Laplace equation meaning Laplace equation Laplacian u equal to meaning that means namely Laplacian of this phi of x is equal to 0 for x not equal to 0 and then this phi is given by this, okay, for n equal to 2 and for n. So now you can see what I have solved the same fundamental equation with some constant c1 c2. If I take c2 0, you can take I can take c2 0, that is a different story, but these are the, you know that the solutions, the harmonic functions are this c1 log r plus c2 c1 r to the power n minus 2 plus r is nothing but mod x, right? So with this motivation in mind I define a new function, a phi x, which is defined in this way and we call this is, and for x not equal to 0 that has to be very careful, you have to be very careful. For x equal to 0 it is not defined, so we define a function phi x as these equations. So this by log x. Why this constant comes? This is a different story. Okay, this I cannot explain you now because there is something called Dirac measure. So because this constant, this peculiar constant comes, this n into n minus 2 into alpha and all this peculiar constant comes because of some different reason. Okay, but this is not a very important thing because you can name it as Cn is a constant. Just you take C2 equal to C1 and C1 are the constant, dimensional constant, okay? Because it only depends on the dimension. See, n equal to 3, 4, 5, n equal to greater than equal to 3, this is a n equal to this is a constant, okay? A purely a constant, this is a dimensional constant. So this counts because of a fact is that this I have said that Laplacian of phi x equal to 0 for x not equal to 0. In general, you can write something like that. This you will not understand now. In general, you can write Laplacian of phi of x is some Dirac measure. You know some Dirac measure at the point 0. Okay, sorry. Dirac at the point 0. Okay, so because the what is Dirac at the point 0? If x is not equal to 0, this is 0, right? Yes or no? If x is not equal to 0, Dirac, no Dirac measure, right? Everyone knows, right? Yes or no? Do you know Dirac measure? Have you studied in measure
Yes,
theory?
sir.
Everyone knows what is the Dirac
Yes,
measure,
sir.
right? So what is you just forget about this part. You just forget about what is Dirac measure at the point. So at x, when x equal to 0, this is 1 when x equal to 0 and rest it is not equal to 0. Okay. So but you have to understand I am differentiating a function and I am getting a measure. So this equality, how this equality makes sense. So I am differentiating a function and I am getting a measure. This is something very, very peculiar, and it's completely not intuitive, right? Counterintuitive, because I am differentiating a smooth function, I am getting a measure. What is this nonsense, right? There is a very much sense. There is that. This is known as distribution theory. Okay, it was invented in late 1950s or 60s. 1950s by Lawrence Schwartz. For that, he also got a Fields Medal. Okay, distribution theory. This is called distribution theory. This is one of the fundamental theory in modern theory of partial differential equation. Okay, but you don't have to understand this. Okay, this is a very modern theory. That is in a different course. We have a modern theory of partial differential equation. There is some different course, so you don't have to understand. So that is why this, because you have a delta Dirac at 0, for this equation to satisfy, the constant was chosen like that. Okay, that is the reason I have taken this type of constant. So you don't have to bother this constant. Why this explicit constant come for you? This is a constant some Cn. Okay, and this is some constant C1. Okay, so for you, Laplacian of P, Laplacian. So just a minute. What happened? So somehow it deleted. So Laplacian of P of x is equal to 0 for x not equal to 0. And that function, and this function is known as fundamental solution. Okay, clear? You just now tell me, is that clear or not? You can ask me, please. Please. So there is some problem near origin. Okay, so that you have to understand because of 1 by mod x and all those things.
And also we are not defining it for n equal to 1 and
No, not because how can we do? Because it is a Laplacian. Laplacian it cannot be for n equal to 1, right? Because at least for Laplacian, at least 2 is needed, 2 dimension in there. Right? Otherwise, how can I talk about the
yes.
partial derivative x and y, right? So, okay, is that clear? So there is, so you just argue that there is some problem at x equal to 0. Okay, so we don't have to understand that point. So what is that? For x not equal to 0, I define this is a nice function. For x not equal to 0, you can define, and you can check easily that this satisfies this Laplacian of Px equal to 0 for x not equal to 0. And this why so I explain you why this constant comes. This constant comes because of some very deep result known as the Dirac. So this is known as the distributional derivatives. Okay, you don't have to. This is your classical sense. Laplacian of Px equal to 0 for x not equal to 0. That's all. So this function phi is known as the fundamental solution. Okay, because this is a very fundamental. That is why its name is fundamental solution. Okay, fundamental solution. Now we will do just a theorem regarding this fundamental solution, and we want to solve. This will give you a solve of a. I will solve a PDE using this fundamental solution. Any general PDE in Rn, this Laplacian. So our main aim is to solve this type of equation, right? Laplacian u equal to f in Rn. First of all, whether it is solvable or not, whether for which type of f this you have a solution or not, that we have seen. Okay. Now we want to study. We want to study these equations. Laplacian of u equal to f when f is a non-zero, and some more regularity I will assume on f. Okay, this is just today I will do just one theorem. Okay, this is a very big theorem and it's quite complicated. So there are a lot of analysis I will use. Okay, epsilon delta estimates and I will use. Okay, please ask me whenever you have a doubt. Please, Kritika, Atharva, Shushil, Shammi, Ankit, Ekans, Anshu, and Navneet. Please ask me whenever you have a doubt. This is a very serious and difficult theorem. Okay? Clear? Please follow this theorem. It will not be. I will explain each and every step. Okay? And just see the. Okay. The theorem is. It's a very simple looking theorem. Just today I will do one theorem. Let your given f is a C2 CRN. What does it mean? Anyone? What does it mean?
A function with compact support on.
And C2. It is a function with compact support C and it is a C2 function. Is that clear? That means outside a compact set f is 0 and function, the regularity function is C2. That means its second derivatives is continuous. All its second derivatives are continuous. Clear? Then I define a function. How I define? Phi convolve with f. What is this phi? Phi is a fundamental solution. Phi is this phi. N equal to 2, this is n equal to 3, this is your phi. I convolve with a given f. Then what you will, and this is a C2 function, C2 of R. It's no complex support. Okay, this is a C2 function, and this is very important and solves this equation. See how beautiful is this thing. You always know what is the solution of the equation Laplacian u equal to 0 when u is radial. These fundamental solutions. Okay, you just now you want to solve this type of function. If f is a continuous function with compact support, you just convolve with phi. Okay, you just convolve with phi. Then if you take the Laplacian of u, then it is f. And this is a C2 function. So this solves your equation. Right? Yes or no? Yes or no? You want, so your main idea, how for a given f I want to solve Laplacian u equal to f. So here if I said that some regularity of is needed, so you just take a function, a simple function with compact support C2 function. Then you just convolve with this fundamental solution. You will get Laplacian u equal to f. This solves your equation. See, and you, what is phi? Phi is known. This is your phi. You convolve with your given f. So this is your u. You define, you convolve with it. This is you define u. Then Laplacian of it. This is a one solution of this equation. There might be many other solutions, but this is one of the solutions. Is that clear? All of you?
Yes, sir.
So this, I am not saying that all the solution will be of this form. No, I am not saying this. All the solutions of the Laplacian u of u will be is given. I am saying that this is one of the solution of this PDE. That if you define u is as phi convolution with f, then Laplacian or minus Laplacian of u equal to f. This solves your PDE. Okay? Clear? Okay. Now the proof is not very difficult. There are a lot of real actually analysis we'll see. This is the, you will see how major theory, everything will come into play in the proof. Okay, before that let us remark something. Okay, before proving, I have to prove this. Before that, I remark something. Okay, and your phi, what is phi? Phi of x, just see some properties of phi of x, the fundamental solution, because it will be required. Mod of x when x n equal to 2, this is 1 by, some constant, Cn by mod x to the power n minus 2 when n greater than equal to 3. I say that, first remark, phi is locally integrable. What does it mean? What does it
That
mean?
it is integrable on every bounded set.
On a compact set. Phi is locally integrable means integral of phi, modulus of phi dx is finite for every compact set. Every compact set in Rn. Clear? Okay. Now you tell me. I choose, it is enough if I consider this compact set. Is that clear? Why? Huh? It is enough if I choose this compact set, mod x less than equal to 1. That means I choose a compact set. Of course, this 0 is, it is not defined at 0, but I choose a compact set. Is that clear? Why? Yes or no?
We can normalize it.
Normal, what normalize? You just take any only difficult. You have a problem. This function has a problem near origin, right? Otherwise, this function is a very smooth function. If I take some compact set not containing the origin, then this 1 by mod x is a very nice function. Yes or no? You just take the this is a bounded function, mod x, 1 by mod x or log of mod x on a compact set which does not contain origin. It's a very smooth function. It's a very, so bounded function. You take the supremum out. It's only a compact set. Is it integrable? Yes or no? One did not understand. Did you understand? See,
Yes.
1 by mod x log mod. What is the problem? You can say this is x not equal to 0, but it has also a problem near origin, right? It can blow up near origin, right? Log of mod x or log of mod x in minus 2, right?
Yes.
Right. So I have to check the integrability near origin. If I take this compact set which does not contain origin, this 1 by mod x is a nice function, n minus 2 or log mod x is a nice function on any compact set which does not contain origin, right? Then it's I can take this is a bounded function less than equal to some c1 greater than equal to some c2. It's a very nice function on any compact set, okay, which does not contain origin. The only problem is if a compact set containing a origin, then I have to check whether this is integrable or not, right? Okay. So this is phi x. So this is I just take as constant. This 1 by 2 pi is a constant. First I take n equal to 2 case. Let's take mod x less than equal to 1 log of mod x. So this I can write. You can use the polar coordinate. You remember polar coordinate? Yes or no? This I can write 0 to 1 log of 1 by r dr. Of course, w1 is outside. 0 to 1 log of 1 by r dr. This is integrable or not? It is integrable or not? You did not understand. You just tell why I have written like this. Who will tell me? Pritika? Why I have written mod of log of mod x is log of 1 by r 0 to 1 w1 r dr. Why?
By changing into polar coordinates, f mod x
Yes.
can be written as
Yes.
f
So del
r
b
r
r
n
del
minus
b
1.
0 r. You remember del b 0 r, and this I have written as r equal to 0 to 1. You remember f of r to the power n. So dr d theta, right? Now you remember del br I have changed it to del br to del b 1. So this
0
is
1.
0 1. Yes, this is so w1 comes and fr, and this the r will be changed with r to the power r to the power n minus 1 dr. Here n equal to 2, so r dr d theta. R fr r dr d theta. And what is d theta? D theta will be the integral on del b 0 1. And this is the integral del b 0 1. So fr is a does not depend on theta. F is a function, radial function. This does not depend on theta. So r dr fr comes out. So this is 0 to 1 fr r dr, and this is d theta. And what is this? This is w1. So this is w1 into 0 to 1 fr r dr. Clear? And what is your fr? Fr is log. This I can write as mod x less than equal to 1 log of 1 by mod x, because I have, you know why I am writing this, because I have taken the modulus log of 1 by x. Okay, so this is, so is that integrable? 0 to 1 log of 1 by r into r dr. Is it integrable? Yes or no? Yes or no? Is it integrable? You don't know how to check this. Only problem is 0. Near 0 log of 1 by r goes to infinity, or minus, infinity, and r goes to 0. But whose growth is more, log or r? Whose growth is more? So log 1 by r into r will go to 0 as r tends to 0, right? So this is integral. Clear? Is that clear?
Yes, sir.
Log x, whose growth is more, you know. Okay. Now for n equal to 3. Sorry, n equal to 3 or n greater than equal to 3. अब बोलो क्या होगा? Who will tell this? What in polar coordinate, what I can write? Now you have to tell me. Who will tell? Shammi will tell. This integral, what I can write in polar coordinate? Shammi, tell me what I can write.
Like again, integral of r from 0 to 1, some constant, and then
Wn minus 1, some
w-
constant. Then
1 upon r, just
1 upon
r,
r. N minus 2 is there. So
and then because we are converting that r and minus 1 will cancel out.
ठीक है? Is that clear? This comes the r to the power n minus 1 dr d theta. D theta comes here. The function is your this. Clear? So this is a constant c tilde I am writing. 0 to 1, n gets cancelled, r dr. This n cancels. It only one step left, r dr, which is finite. Is that clear? Shammi, is that clear?
Yes, sir. Like I just cancelled out another way. So that's what I'm saying.
Okay. So phi is belongs to L1 of log, like this it is written. Rn. Because I will be using in the proof. That is why I am saying this. Remark 2. Remark 2. What is gradient of phi? So we just take the gradient. If you see that this is x by mod x square. If n equal to 2, this is the constant. I am writing Cn minus Cn constant x by mod x to the power n. If n greater than equal to 3. Okay? So just check. What is that? You just take the gradient here. It takes the gradient. It takes the gradient. You just take the gradient. Okay? Take the gradient. So you will get this. Now I am claiming that. So what is modulus of gradient of Ex? This is nothing but a constant 1 by mod x to the power n minus 1 for n equal to 2. Because if you take the modulus, so it will be, if you take the modulus, so this will be 1 by mod x. And if you take the modulus, this will be 1 by mod x to the power n minus 1. So you can write for n greater than equal to 2. This is the, again clearly, if I do again less than equal to 1, gradient of Vx. What will be this? dx. This is a constant Wn minus 1, 0 to 1, 1 by r to the power n minus 1 into r to the power n minus 1 dr. This gets cancelled. This is Cn Wn minus 1. This is 1. Okay? So again, this imply gradient of phi x is also L1 log for n greater than equal to 2. Clear? So summary, what the remark says that first of all, this phi is L1 log of Rn for n greater than equal to 2. And also I have proved that gradient of phi is also L1 log of Rn for n greater than equal to 2. These I will be using in the theorem. Okay. Okay. Now again recall the theorem. What we shall want to prove, that given f is in C2C of Rn. Okay. Define a function u which is phi convolution f. Then this phi convolution f is a C2 function. Very nice C2 function. And it solves Laplacian of u is equal to f of x for all x in Rn. So this I got a one solution of this equation if f is in C2 of Rn. Okay, now we want to prove this. Okay, proof. First we want to show that proof of theorem. First we want to show that what I have to show, u is what is that, phi convolution f. So this is a fundamental solution and this is your given function C2. First of all, we have to show that whether the function u is well defined or not. Whether u is well defined. Because this is a new function I am defining, right? Well defined. Then we have to show that this is a C2. Whether u is well defined or not. Okay. Phi convolution f. Let us check for each x whether this makes sense or not. This is Rn f of x minus y phi of y dy. Whether for each x this is finite or not. Take the modulus. Take the modulus. This is Rn phi y mod of f of x minus y dy. What is that? X minus y. What is the support of x minus y? Who will tell me? F is a CC function. Compact support defined. But f has a compact support. But what will be the support of x minus y? Because x is some fixed x, y is a support. So the support of this function is some
translation.
Exactly, x plus k, which is again a compact set. Yes, this k is a compact. X plus k is also a compact set, right? Am I right? Yes or no?
Yes, sir.
It's again a compact set. So I define as kx subscript x. Okay, so this is nothing but some kx phi of y. I take the supremum of output, supremum of f, which is some m, let's say m. Okay, which depend on x, of course, m. So dy. So what I got is that f convolution phi of x modulus is less than some m which depend on x integral in a compact set. Is that finite? Why? Is that finite?
Yes, sir, because phi is L1. So
Exactly. So this is some c of x, some constant time which is finite. So for each x, f con x in Rn, f, that is why, see why there's a very important remark, why I need f to be a L1, phi to be a L1 log. So this each one, this is belongs to, this is well defined. Well defined. Okay, very good. Now your u is a well defined function. So in that way, phi convolution. So we know that f convolution phi is equal to phi convolution f. There is well defined. Now what I have to prove? I have to prove that u is C2 of Rn. Yes or no? I have to prove u is a C2 of Rn. For that, what I have to do? What I have to do?
We have to prove the existence of second order derivatives.
First of all, you have to see the first of all derivative. Let's see. U of x plus HEI minus U of x by H. What is that? We know in convolution I have done many times. X plus HEI minus y minus f of x by H p of y dy. Now tell me, as limit h tending to 0, why this limit will go inside? H ei minus y minus f of x by h py. Why? Limit goes inside. Ei minus y minus f of x. And this is nothing but if this goes, so this is derivative of f, right? Del f by del xi. X minus y phi y dy. This is nothing but phi convolution del f by del x. Who will tell me why this goes inside?
So like say we have fixed x, so like f of x plus HEI minus y minus f x will have again compact support.
Some
So
complex.
then I can use so then I can use the mean value theorem to, like, since I know f is c to c, so then from
C
there,
for-
like I can bound and use DCT.
Yes, excellent, excellent, excellent. Use DCT and mean value theorem. Excellent. And using the fact that f is C2.
And it's like after that we use that 5i has again
Excellent,
L1 log.
excellent,
So
excellent, excellent, excellent. Good, very good. Correct? Got done. So these imply del u by del xi exists. Similarly, since f is a C2 function, the same logic will work for this one. Del square, del xi, del x. Yes or no? This will be phi convolve with del square f by. Yes or no? Huh? Same thing. Now you apply on del f by del x. Yes or no? What happened? Yes or no?
Yes.
Same logic. Same logic. DCT and all this. Mean value theorem. Same logic. Similarly, this also. Now, all xi xj exist. All xi exist. So is a double derivative exists. Now what I have to prove? To prove u is in C2, the double derivatives are continuous, right? To prove u is in C2, consider a sequence xn converges to x, then phi convolution xi del xj xn converges to phi convolution del square f by del xi del xj x. Why? This is why? Why? Because f is
C2, like C2C, and then on compact sets we have
exactly.
like phi composed with that is again become a continuous function. So
exactly, and these imply del square u by del xn by del xi. Very good. Del xj will converges to del u. If you understand each and every step, things are very easy. Just question yourself whether this is true or not. That's all. So this proves that these three steps proves that u is in C2 function. What is u? U is in phi convolution f. Okay. So first step is done. Now the difficult part. Now we have to show. Now we claim that claim that Laplacian of u minus of u is equal to f of x. X in Rn for every x in Rn. This is a difficult one. Okay. So for that you have to blindly take Laplacian of u. What will be the Laplacian of u? That is I equal to 1 to n del square u by del xi square. In terms of convolution, what can I write? Tell me. Huh? Please tell me. U is your phi convolution f. What I can write? Huh? What I can write? I know I can throw the derivative to
Phi
phi f
F.
f f f. This is summation. I can write I equal to 1 to n phi convolution del square f by del xi square. So this is nothing but Laplacian of u is I can take the summation inside I equal to 1 to n del square f by del xi square. And this is nothing but phi convolution Laplacian f. So Laplacian u is nothing but phi convolution Laplacian of f at the point x. Just straightforward. From the definition, using definition of convolution. Now we have to show that this is equal to minus f of x. Then we are done? Yes or no? Then we are done? Yes or no?
Yes.
Yes, sir.
Then we are done, right? Okay. Now you write down what is this phi convolution. This. So Laplacian of u of x is nothing but some compact set Br. I will tell what is that. P of y Laplacian of x minus y dy. What is Br? Who will tell me? F has a compact support. Whether Laplacian derivative of f also have a compact support, yes or no? If the function is a C2 function, if f has a compact support, then its derivative and the double derivative all has a compact support, yes or no?
Yes, sir.
Of course, just the definition of a support. And what is Br? Where Br is a large ball. So like this lies. So you have this function y going to f of x minus y. As you said, this will have a support x plus k. So it is like this is x plus k for each x. So I have here is for each x. Laplacian u at the point x. X is your fix now. At Laplacian u evaluated at the point x. This, so I take a big ball of radius or centered at origin, radius r, so that it contains the support x plus k. Agreed or not? What is that Br? All of you agree? Huh? Kritika, Ankit, Anshu, Navneet?
Yes.
Hello, sir, could you please explain once again?
Okay. This function f has a compact support. Clear? So as you said, f of for each x minus y is a function, each x is a fixed x. It is also has a compact support. Huh?
Yes.
K. This is has a compact support k. Then what will be the support of fx minus y? X plus k. Clear? So this is also a compact set. The compact set for each x. Fixed x, this x plus k is a compact set. Yes. So Laplacian of f has a compact support. Has a compact support. The same set k has a compact support. Because you say that if f is compactly supported, this derivative is also as a compact support. Second derivative is also, if it is C2, then its second derivative has also a compact support. Yes or no?
Yes.
So Laplacian of x minus y, x minus y also complex about x plus k. So the x plus k is a compact set. It might be like this or somewhere like this, sitting inside Rn, right? Closed and bounded. So I take a bigger ball, a radius r, so that it contains this set, this complex x plus k. This can be possible. You can choose r very large so that you can take a very large ball centered at origins and take a ball so that this compact set contain in that Br. Is that clear or not?
Yes, sir.
Yes. So same thing I am writing. So this is that Br. What is this Br? Br is the set containing the compact support of x plus k. Clear? This I can always do in a symmetric way. Symmetric way means I can take a bigger radius of bigger radius r centered at origin so that it contains the compact set. Okay. So now your Laplacian of u of x is nothing but now this is Br phi of y Laplacian of f of x minus y dy. We want to claim that this is equal to minus f of x. I have to show this why this is equal to minus f of x. Okay.
Sir. Sir, when we are calculating the convolution, we'll have to integrate whole Rn.
Yes, all Rn because it has a compact support. So
okay, sir. So
because Laplacian f has a compact support, so it will vanish, right?
Okay, yes.
It will vanish for each x. For each x, this Laplacian f because outside x plus k, the support is x plus k. Outside x plus k, the compact set integral is 0. So I'm not writing. So if you don't want, you can write Rn. No problem. Okay. Okay. Now what I will do? This is your bigger ball Br. So suppose if I do the integration by parts and throw the derivative to phi, where is the problem? Phi has problem where?
Near origin.
Exactly. Otherwise, Laplacian of phi is 0, right? If y is not equal to 0. Yes or no?
Yes.
Your life is very easy. Just throw a derivative Laplacian here. Laplacian of phi. But the problem is I cannot throw it because there is one point. Y where it is non-zero. Right? So wherever there is a problem at origin, there is a problem. You cut that origin. You take with epsilon. We will see what happened near origin and we will see the set here separately. We will cut the set in two parts. This Br I cut the set in two parts. One part is this annulus portion, another is this portion. Okay. Okay. This what I will do, this I can write as P0 epsilon plus, this is the analysis, this is the beauty of analysis. Wherever there is a problem, singularity, that we call it singularity, wherever there is a problem, we cut that portion and we'll separately see what happens here. Okay. So this integral is equal to integral over B0 epsilon. Agreed? Agreed or not?
Yes.
Okay. This I name it I1. This I name it I2. Okay. Let's see what is I1. I1 is where I cannot throw the derivative because phi is not defined at integration is defined but not in a pointwise sense, right? As I said, phi is a local integral. Now you tell me where this will go if I take epsilon tending to 0. Where this integral will go if I take epsilon tending to 0. हाँ कहाँ जाएगा? Where this integral will go? Where it will go? Who will tell this? Kritika? Where this integral will go? As epsilon tending to 0, that means the measure of the set is, what is the measure of this set? The measure of is some constant time epsilon to the power n. As epsilon tending to 0, this measure is going to 0. So the set is very, very small. So the where this integral will go? Measure theory. Where this integral will go?
0, like
Exactly 0. Why? Remember in measure
like
theory.
real big, like we can
Measure theory. If a function f is a L1 function, you can, there always, for any given epsilon, there exists a delta positive such that this integral measure is less than epsilon whenever the measure of m is less than delta. That means in a small measure set, if f is a L1 function or L1 log function, this integral is small. For any given epsilon positive, you can always find a delta such that integral mod of f, if f is in L1, this is important, otherwise not. So since phi is integrable, Laplacian f has a compact support. So this function is a L1 function, locally L1 log. This is a L1 log function. You can take the supremum of Laplacian of fx out, integral b0 epsilon phi 1, right? So this is an L1 function. Since the set is going, the measure of the set is going to 0, so the integral will also go to 0. Okay? It goes to 0 as epsilon goes. So here I have used crucially the fact that p is L1 log. Otherwise, I cannot claim that this function is a L1 function, L1 log function. Is that clear? Everyone tell me, is that clear? क्या हुआ? Is that
Yes,
clear? All of you?
Yes.
All of you?
Yes,
Navneet,
sir.
Ankit, Shammi,
Yes, sir.
Atharva? Clear? So you know that in a small measure set, if the function is a integrable function, on a small measure set, the integral is small, right? So same thing, as this integral will be small in a small measure set, as I am taking epsilon tending to 0, this integral will go to 0. Okay. So we are done with that part. Now what remains? So Laplacian of u of x is nothing but limit epsilon tending to 0 PR minus P0 epsilon P of y Laplacian of x minus y dy. Now let us concentrate on this set. Then I will take epsilon tending to 0. Clear? Okay. What is this set? PR. Here in this set, because only problem phi has at 0. Otherwise, phi Laplacian phi is a 0 function, right? Laplacian of phi is P of y is 0 for y not equal to 0. Is this set contain 0? Br minus B0 epsilon? Forget about epsilon tending to 0. For fixed epsilon positive. Is that set contain 0?
No, sir.
No. This I can write as like this. I will use integration. I will take the derivative here. But the problem is the boundary term will come. Right? I'll tell you. Don't worry. Py. del square by del yi square f of x minus y dy. I first use the integration by parts. First derivative goes to here. So you have here epsilon. This is r. What are the boundary? What are the boundary of this set? What are the boundary of this set? This is
like inner and outer
this two.
circles.
So at the outer boundary, what is del f by del y at the outer boundary? Huh? क्या होगा?
It's 0.
0. Very good. Because the
It's
compact
complex up
set is here.
inside.
Yeah. But this boundary, something will be there. So first derivative here, minus I equal to 1 to n. This is br minus b0 epsilon del phi by del y I into del f, first derivative, yi x minus y dy, plus only inner boundary will come, plus I equal to 1 to n del b0 epsilon phi y del f by del yi nu I d sigma y. Clear? Okay. Again, I will throw this derivative to here. Again, integration by parts. Again, this boundary will come, right? With f and phi. Again, I use integration by parts. अगर मैं इंटीग्रेशन बाई पार्ट्स करता हूं तो मुझे मिलेगा दिस इज समेशन आई इक्वल टू 1 to n br b0 epsilon del square phi y by del yi square f of x minus y dy minus summation I equal to 1 to n del b0 epsilon del phi by del yi, ये तो पहले लास्ट दिस न्यू आई प्लस just check the integration by parts. D sigma 1. Is that clear, all of you? I use the integration by parts, this set on this. This is one boundary here, no? This. So the derivative will go here, del square phi by del y square. The boundary term will be del phi by del y, del yi, and f of x minus y nu y. So this is the term. Del phi by del y, f of x minus y nu y dy. Clear? Now I take the summation, nu y will be there. So del f by del y. So what will be this? Del phi by del yi nu y. I equal to 1 to n. What will be this equal to? हाँ क्या होगा? Del phi by del nu. This is ith component. Every component will come. Del phi by del u is nothing but summation del phi by del nu I yi into nu I. So take the partial derivative in the projection to nu I. Is that clear why this comes? Yes or no? This is all the partial derivative, right? This is a gradient of phi dot nu. What is it? What does it mean? Del phi by del nu. Yes or no? क्या हुआ? What happened? What is gradient of phi dot nu? This is nothing but this del phi by del y dot nu I. What does it mean? Del phi by del the gradient vector dot nu. That means you take the projection of the gradient vector along the that is the directional derivative del phi by del nu. Yes or no? Is that clear? Ankit, Atharva, clear? Shammi, clear?
Yes.
Okay. So if I write down this, you will end up with this. Just let me write down that this is equal to BR minus B0 epsilon Laplacian phi of y f of x minus y dy minus del B0 epsilon del phi by del nu f of x minus y d sigma y plus del B0 epsilon phi y del f by del nu x minus y. Sorry, that is equal to a minus b plus c. So this is a, this is b, this is c. Okay. What is your a? Immediately, who will tell me immediately? What is a?
0.
Because Laplacian phi of y equal to 0 or y not equal to 0. So this is 0. Now you have to remains are b and c. Let us first concentrate on c. Modulus of c is nothing but phi y. You are almost done. Okay, this is take the modulus inside, so less than del b 0 epsilon phi y del f by del nu x minus y d sigma y. Sorry, so this is bounded less than equal to m. Why? Why?
F is like C2, so like C2C, so
Because del f by del f has a compact support. All is derivative
yes.
C2 function. So all is derivative. Whatever direction you take, nu1, whatever direction you take, directional derivative will be bounded. Yes or no? It has also a bound compact support, right? Less than m into del b 0 epsilon. Sorry, this is a modulus d sigma y. So what is this? Into this is into c time. You just integrate. You know what is phi epsilon. So epsilon. So this is nothing but c into log epsilon into epsilon if n equal to 2. C into epsilon to the power n minus 2, epsilon to the power n minus 1 if n greater than equal to 3. Why it comes? Anyone? Anyone? What is phi, man?
P is radial, so
Yes,
it is
radial.
constant on the
Only
boundary.
it is on the circle, so it is on the circle. So epsilon comes out only integral del b 0 epsilon. What is the measure of b epsilon? Epsilon to the power n. Yes, epsilon to the power n minus 1. Okay. So for every n 2 or n, this goes to 0 as epsilon tending to 0. Clear? So this term goes to 0 as epsilon tending to 0. So C is also 0 as epsilon. So this part also goes to 0 as epsilon tending to 0. This is all equal to 0. So as epsilon tending to 0, this goes to 0. Now you concentrate on B. Okay? What is B? Write down B. B is del B 0 epsilon del phi y by del nu f of x minus y d of sigma y. This I write like this. Del p 0 epsilon del phi of del nu y. You write down f of x minus y minus f of x plus f of x plus and subtract f of x d sigma y. Okay, clear? ठीक है? So I take this. So I take f of x. This is a constant. Del b 0 epsilon del phi y by del nu d sigma y plus del b 0 epsilon f of x minus y minus f of x d sigma y. Okay? I have done nothing. So you concentrate first here. You take this. So this is equal to f of x del b 0 epsilon del phi by del nu. So del phi by del nu, I have said this is a gradient of phi dot nu d sigma y. What is nu for del b 0 epsilon? Who will tell me? What is nu?
Minus y by mod y.
Minus y by epsilon. X by mod x. What is mod x here? What is mod y? Yes, minus y by mod y. What is mod y here? Because it is on the boundary. So what is mod y?
Yes, epsilon.
Epsilon.
That is right. Gradient of phi dot minus y by epsilon d sigma y. Okay? Is that clear? Okay. Now integrate. You know gradient of phi. You remember? I have done that. Gradient of phi. This is some constant or something. It comes like wn minus 1 by mod y to the power n minus 2 into 1 by epsilon d sigma y. Mod y equal to epsilon. Okay? This minus comes out. Okay? Is that clear? What happened? Is that clear? I have calculated it. Gradient of phi of x. I have calculated it, man. Some constant
Yes.
type mod x. So now you have gradient of phi dot y. That is dot this gradient of phi dot y. So that will be minus mod y square by mod y to the power n minus 2. So that is why I get n minus 1. That is why I get n minus 2. Is that clear? What happened?
Yes, sir.
So this is minus of f of x by wn minus 1 mod f epsilon. This 1 by epsilon comes out. So integral mod y equal to epsilon d sigma y. What will be this epsilon? This is a measure of del b 0 epsilon. That is epsilon to the power n minus 1 into wn minus 1. Clear? What is wn minus 1? Del b 0 1. Clear? Del b 0 epsilon is epsilon to the power n minus scaling. Is that clear? Yes or no? This is a measure of a ball, not a ball, just the circle, the surface measure of the circle of this is nothing but this is del b 0 epsilon. What is the measure
Yes,
of
sir.
del b 0? This is del b 0 epsilon to the power n minus 1 into wn minus 1. So this cancels out. You get minus of f of x. So from this integral I get minus f of x. And the rest is this. So where that integral should go? Any idea? The rest is del b 0 epsilon del phi by del nu f of x minus y minus f of x d sigma y. This will go to 0 as epsilon. Use continuity of, because f is a continuous function. X minus y minus x. What is x minus y minus x? Modulus is xx mod y. So mod y is actually epsilon. So this is epsilon. As epsilon goes to 0, this will go to 0 using continuity of f. Clear? Is that clear?
Yes.
Clear? This goes to 0. So you got, it's a very difficult theorem. F of ux equal to. I hope Each and every step I have tried to make you understand. I hope you have understand it. So go to your home. Please, I'm requesting you. Please go and check each and every step. Then only you will understand. Don't see my notes. I will upload today the notes of both the classes. So I will upload my notes. Plus, please don't try to see. Just do it. Try to do it yourself. If you stuck, then you will see. Okay? This is the hard theorem. Anyway, so we have solved one of the most hard theorem in this course. That minus Laplacian of u equal to f minus f is equal to fx. Is that clear? Kritika, Atharva, Shammi, Ankit, Chitram.
Yes.
Okay. Okay. ठीक है. Anything else you want to ask me? Anyway, ठीक है. Thank you. So we will meet on next Thursday, I think, because Monday is no class. Okay. Thank you.
Thank you.